data analysis. This is the
second of two
videos looking at how you can analyse primary data that you've gathered as part of your research. In the first video, we talked about how you can analyse quantitative data, numbers, for example, data you might get from a questionnaire, to show or describe what it represents. And we talked about a number of calculations like the averages, the standard deviation, percentages, and charts. We also hinted there that it's not simply a case of using your questionnaire to describe what your sample found, but maybe it's possible to generalise your findings to say that they represent the whole of the population. And we talked about a way of looking at the data, and then that there was a possibility of doing some statistical test to see if it was actually significant. Firstly, we need to remember that the size of the sample is crucial. If we don't have a large enough sample, we can't possibly expect it to represent the population. But we can use inferential statistics to look at the likelihood. And then in the second video, we talked about qualitative analysis. How would you analyse your data from an interview or from a focus group or that had been written down? So whether it was spoken or written, how will you make sense of that data? And we talked about breaking it down into different themes and then organising those into different groups so that we could make sense of the qualitative data. In this video, you want to focus on inferential analysis. This is going back to what we mentioned in the first video. We have quantitative data and we want to see if we should expect this to be true for the population, and is it statistically significant. In the example in the first video, we had a table looking at the income of men and women, and we said that looking at that, men tend to earn more and women tend to earn less. It gave us a picture that perhaps men earn more than women. But remember, we said we needed to do a statistical test to actually find out if that's true. So this table allows us to decide which test we need to do to see if that is a statistically significant difference. Along the top of the table, it talks about normal data. In the first video, we talked about the normal distribution. And remember, the normal distribution looked like this, where the data forms a bell-shaped chart with very few responses at the very low or very high ends, and most of the responses clustered around the centre. In order to get this sort of data, we need to have interval or ratio data. In other words, number data that has categories that are equally separate. So maybe if we've coded the response and rated it 1 to 5, for example. Intervals between those numbers allow us to work out how much better something is than something else. If your data is not normally distributed, but it still has numbers, it might be age, or it might be blood pressure, for example, but it isn't normally distributed, then the middle column will give you an indication of which test you should conduct. Or if your data is in categories, perhaps the way people arrive at work, by car, by taxi, by train, by bus, those are categories. So if it's categorical data, descriptive data, or data that has just two possible options, then we would be looking at the final column. So all we need to do if we're going to compare the data to see if it's statistically significant is to decide what we want to know. Do we want to compare our data with what we would expect? Or do we want to see how strong the relationship is between two different factors? Do we want to compare two groups? Or do we want to look at more than two groups, 3 or more groups? And using the table, we can decide which test we need to do. In order to understand the response to the test or the answer to the test, though, we need to understand a few things. Firstly, probability. We're quite familiar with probability. It's very much like percentages. If the probability of something happening is 100%, that means it will definitely happen. If the probability of something happening is 50%, then there's 50% chance it will happen and there's 50% chance it will not happen. So there's an equal chance of it happening or not. If we have 0% probability, then there is absolutely no chance something will happen. So the closer to 0, the less chance of something happening. While we're bearing that in mind, we also need to consider variables. Variables are things that can be measured, whether they're factors or opinions and so on. So any response that we can measure is a variable. And there are two types. Dependent variables, and these are things that can change as a result of something else. For example, your strength might be determined partially by your gender. Men tend to be stronger than women. So your strength is dependent on your gender. The opposite is an independent variable, and this is a variable that does not change as a result of something else. So using the same example as before, although your gender may affect how strong you are, your strength does not affect your gender. Just because you're strong, you don't suddenly become a man. So your gender is independent of your strength, but your strength is dependent on your gender. A couple more terms we need to talk about. We need to talk about hypothesis, and it's a term we use in everyday life. Hypothesis is what you expect to find. Now, if you was doing a test, you would assume that you're expecting to find something, a difference or a change caused by your research. So your hypothesis, written H1, is that there is a difference or a change as a result of what you're investigating. Because of proof being very difficult, we also need to write a null hypothesis, which is the opposite of a hypothesis. And that's the thing that we use to decide and to test. So the null hypothesis is the opposite of what you expect to find. Because you expect to find a difference or a change, then the null hypothesis will always be that there is no difference or no change. So if I'm looking at a cafe and I'm looking at the opinions of staff and of students, then the only reason for testing is if I expect there to be a difference between staff and student opinions, otherwise I wouldn't be checking them. So my hypothesis will be that there is a difference, and my null hypothesis will be that there is no difference between staff and student opinions. Okay, so now I have a hypothesis and a null hypothesis that I can use. And I'm saying that the opinion of staff or students, so the opinion is dependent on the status of the person, whether they're a staff or student. So staff and student become independent variables, and the opinion of them becomes a dependent variable. It depends on whether they're staff or student. Okay, so now I have my hypothesis and I have my variables. Next, I need to decide on the appropriate test. So I want to know if there's a difference in the opinion of staff compared to students. So if I've gathered the data, I will have the count of the different responses of the two groups. So I'll be comparing the averages or the counts, the responses of those two different groups, staff and student. The data is going to be normal. Now there is a test you can do, but for the purposes of this example, we can assume it's a normal distribution. So the test I would need to do is the independent samples t-test. I'm not going to worry about how to put the data into the computer. That's something we can look at in a later video, but I have decided on the correct test. So I would need to get the computer to analyse my data using this independent samples t-test. And the result of that test will give me a probability value or a p-value as to whether or not I've got enough evidence to reject my null hypothesis, which means I can say that my research hypothesis is true statistically. And in order to make this decision whether I can or cannot reject the null hypothesis, I need to compare the p-value against a standard figure. Now, there is debate among statisticians as to what that figure should be, but the most commonly accepted value for social sciences is if the probability value is smaller than 0.05, we can reject the null hypothesis, which means that we can accept the hypothesis. Or to say it in another way, if the probability of getting the results by accident is less than 5%, I can reject the null hypothesis. It's very unlikely. And therefore I can accept the hypothesis that there is a difference between staff and students. Let's look at another example. If I want to know whether time of day has an effect on the quality of the service, I could summarise that information in a table, and in the work activities you will have done a pivot table to this effect. And then looking at that table, I could get an impression as to whether I thought time of day would have an effect on the quality of service. How would I test this? Well, I'm talking about time of day as a variable and quality of service as a variable. And I'm saying that the quality is dependent on the time. So time of day is the independent variable and quality of service is the dependent variable. And then I choose my test. I want to compare the time of day against the quality of service. So again, I want to compare the responses in those categories. But this time I'm going to compare what I found with what I would expect to find. So I'm looking at that first row. And time of day isn't continuous information. In fact, because we've chosen the different time ranges, it's become a simple categorical set of data. They're different categories. And so using this table, I would need to do a chi-squared test to see if what I got is what I would expect or not. So my test is going to be chi-squared, and I input my data into the computer with a hypothesis that there is a difference, time of day does make a difference, and a null hypothesis that time of day does not make a difference. And then I can use the answer that comes out, the p-value, and I can use that to decide whether or not there's a difference. If the p-value is less than 0.05, in other words, if there is less than 5% possibility of getting the result by accident, then I can reject the null hypothesis and accept the hypothesis, which means accept that there is a difference at different times of day. If the probability is more than 5%, then it's getting easier, more likely, that I did get my result by accident, and therefore I cannot reject the null hypothesis, and therefore I have to just accept that there's no evidence of any difference, statistically speaking. So using the table, an understanding of probability and variables, we can do a hypothesis test to check how likely the data is statistically significant.